Let's now take a look at this problem, 2.762 times 603. And the question is to do this using a table of logarithms as opposed to just simply popping out a calculator. So the idea of the problems in this video is to kind of appreciate how things were done, a generation or two ago for doing computations like this. The first step for doing a problem like this is we take the logarithm of both sides. So the logarithm of a base 10 is equal to the logarithm of 2.762 base 10 plus the logarithm of 603 base 10. Okay, so let's take a look at both of these and how these would have been done, say, a generation ago. The first thing we would do is to get a table of logarithms. And I have simulated a table of logarithms using Microsoft Excel. We'll pull it over here. So 2.762, let's go see. So 2.7 is this row here, so I'll mark that in yellow, and 0.62. So that's between 2.76 and 2.67. I'll mark those also in yellow. And so the log of 2.76 I would look up as 0.4409, while the logarithm of 2.77 I would look up as 0.4425. So let me put those numbers down on the computation here. So 0.4409 so that goes with 2.76 and 2.77 would be the other number, which was 0.4425. So the logarithm of 2.762 is clearly in between these two someplace. The way that I would find out what it is, well, it's clearly 0.44 something between them. The way that I would find out what it would be by linear interpolation. So let me find the equation of the line between these. So y minus, using this as my point, 0.44009 is equal to the slope. The difference between these two, 25 minus 9 is 16, so 0.0016. That's the change in the y divided by the change in the x, which is 0.01, times x minus 2.76. And so plugging in x to be 2.762, if I let x be equal to 2.762, we have that y is equal to 0.4409 plus, dividing here, well, I'll do that the last step, so 0.0016 times 0.002 divided by 0.01. So we would have 0.4409 plus 0.0016, and this is 0.002 divided by 0.010, so 2 divided by 10, which is a fifth. So 0.4409 plus a fifth of 16 is 3.2, so I'd have 0.00032, and so adding, we would get that our approximation is 0.44122. So that would be our approximation. And because I'm only good to 4 decimal places anyway, I'll forget the fifth place and just simply put 2 as my approximation. So 0.4412 would be my estimate for the logarithm of 2.762. Now let's come back into the 21st century. If I use a simple calculator to do that calculation, the logarithm of 2.762 would be 0.4412, exactly what I found here by using the table. So the table allows me to find a fairly accurate estimate to 4 decimal places, and actually it looks like here I got 5 decimal places, 122, with only using a table and interpolation. Now let's take a look at the logarithm of 603. So let me clear out the calculations here on the side. Now in days of yore, I would automatically write this as 2 point something. I know full well the answer is going to be between 2 and 3. The logarithm of 100 is 2. The logarithm of 1,000 is 3. So I know that the logarithm of 600 is 2 point something because the answer must be between 2 and 3 someplace. So 2 point something. Now to write this out and to use the table, let's pull the table back again. 603, so I'd go to 603, and that would be this number right here, 7803. So 6.03, 7803, and so that would be my answer, 7803. Now, if that went a little bit too quick, let me go over the justification for that step. So the logarithm of 603 base 10, that's equal to the logarithm of 100 times 6.03 base 10, factoring out 100, and the reason that I factor out 100 and leaving a decimal, that's usually not the way that I would factor, but when I split up the logarithm on the next step, the logarithm of 100 base 10 is something that I can figure out off the top of my head. That's equal to 2. So 2 plus the logarithm of 6.03, which we just looked up on the table, was 0.7803. And so combining, we get 2.7803. And so that's the answer for that. Before we go any further, let me pull out the calculator and check that this actually works. So if I take the logarithm of 603, I do and get 2.7803 as expected. Okay, now I just add these up. So coming back over here, adding up and just being, so I'm going to deliberately do this without a calculator just to go over how this was done in the old days. So 2 plus 3 is 5, 1 plus 0 is 1, 4 plus 8 is 12, so 2 carry the 1, 1 plus 7 is 11, plus 2 plus another 1 makes 2, and then finally carrying the 1 we get 3. So adding these together we get 3.2215. And now we have to go work in reverse. So the logarithm of a base 10 is equal to this, and therefore a will be equal to 10 to the 3.2215. Now that's equal to 10 to the third plus 0.2215, which is 10 to the third times 10 to the 0.2215. Now 10 to the third I know automatically, that's 1,000. The other one, 10 to the 0.2215, back in the old days this was called an anti-logarithm, where I would use the log table but working in reverse. So 2215, let's go see if we can find that someplace. 2215, well, it turns out it looks like it's between these two marks right here. So 2215 is between 2201 and 2227. And that is for 1.66 and 1.67. So let's mark that, 1.66 and 1.67. So 1.66, well, going the other direction, 0.2201. The anti-logarithm of 0.2201 is 1.66. In other words, 10 to the 0.2201 is 1.66. The other mark that I care about is 0.2227, and that corresponds with 1.67. And let me pull this back up, make sure I copy that right. 2201 is with 1.66, 2227 is with 1.67. Okay, now the one I care about is 0.2215. And so I must work in reverse to figure out what the number is over here that matches it. And truth be told, the easier thing to do for this problem would be to do the other direction. So let me put the 1.66 over here and 1.67 and erase over here. So let's find the line connecting these points. So we have y minus 0.2201 is equal to the slope, which is 0.0026, divided by 0.001, or 0.01, pardon me, x minus 1.66. And so we get that the value of y is 0.2215, and over here 0.0026 divided by 0.01 is 0.26 times x minus 1.66. So now it's a matter of just solving. We get 0.0014, subtracting, divided by 0.26 is equal to x minus 1.66. So that x is equal to 1.66 plus 0.0014 divided by 0.26. Now, back in the old days, we would compute that by hand. Let me do this by cheating. 0.0014 divided by 0.26 is 0.0054. Just rounding off to 4 decimal places, so 0.0054. And so x is 1.6654. So we'd have 1.6654 that goes here. And then multiplying by 1,000, we get 1,665.4 as our estimated product. And so that would be the answer to the product. Now let's actually check this with a calculator and see how we did. So the original problem, of course, was 200 and, well, first off, before I check with the calculator, 10 to the 3.2215, if I just simply do that on the calculator, I get the answer that we just had, 1,665. The answer is 0.3. I got 0.4 using the estimation technique. And then the other thing to check is, let's see if we got the right answer, 2.762 times 603. And if all goes well, the answer ought to be about 1,665. And indeed, 1,665.486. So I got the answer to 4 significant digits and almost 5. And so that's how logarithms would be used, analog tables would be used in order to compute a product. Okay, now let's do the same thing again, except this time for an exponential. So the problem in question is 22.83 raised to the 0.25 power. In other words, the fourth root of 22.83. So let's call this one b. If I take the logarithm of both sides, the logarithm of b base 10 would be equal to 0.25 times the logarithm of 22.83 base 10. Okay, logarithm of 22.83. To find that, again, pretending we're back in the old days, we'll use the table. So 22.8, so I have an, let's go to the 22.2, so 2.2 would be on this line. Let me mark that in yellow. And the next digit is 8, so that's between 2.28 and 2.29. I'll mark those in yellow. And so I'm somewhere between 0.3579 and 0.3598. So let me mark those numbers on the spreadsheet. So 2.28 goes with 0.3579. And then on the other side, it'd be 2.29. And the number in the table that went with that was 3598. Okay, the number that I want to have is 2.283. And so I will use linear interpolation to figure out what the log is of 2.283. So y minus 2.28 is equal to the slope, which is the difference of 98 and 79 is, I believe, 19. So 0.0019 divided by the run, which is 0.01, times x minus 2.28. And I made a mistake in writing this. I apologize. This here should not have been the 2.28. That is my x-coordinate. The y-coordinate that goes with that is the 0.3579 figure. Okay, now I plug in x is equal to 2.283. So plugging in, we get that y is equal to 0.0019. Then when I multiply by this, 2.283 minus 2.28 is 0.003, and I divide that by 0.010. So the answer is 3/10 of 0.0019. So multiplying this out, we get 3/10 of that would be 0.00057, just multiplying it out. And clearly I only have things accurate to 4 decimal places, so we have that. And of course I need the other 0.3579 that this gets added to. So adding that to 0.3579 gives me 0.35. Okay, so adding 5.7 on here gives me 8.47. And then rounding to 4 decimal places, it is 0.3585 to 4 decimal places. Okay, let's do a quick check to see if this actually worked out. If I compute the logarithm of 2.283, which is what I just did, the logarithm of 2.283, I get 0.3585, which is exactly what I have here. The 847 is slightly incorrect, and that's okay because these numbers are only good to 4 decimal places anyway. All right, so we got the 3585. Okay, now don't have 2.2, I have 22. Now back in the old days, I would know that this was automatically between 1 and 2 someplace. So it'd be 0.25 times 1.35585. And the reason for that is because the log of 22, let me just up here on the top in green, the log of 22 is the same as the logarithm of 10 times 2.283 base 10, which then splits up as the logarithm of 10 base 10 plus the logarithm of 2.283 base 10. So logarithm of 10 is 1, logarithm of 2.283 we just got done figuring out, so 1.3585. And let's figure this out and make sure I actually got the right answer. If I take the logarithm of 22.83, not surprisingly, I get 1.3585. Here I had 0.3585. Okay, so the next step is to figure out what 0.25 times 1.3585 is. Now, this could be done with logarithms, or you can just simply multiply it out. This one is not too bad to figure out. 1.3585. I'm multiplying by 0.25, which is the same thing as dividing by 4. So 0.3, 12, 15, get another 3, 12, 3, 8, gives me 9, 36, 25, and then 625. And again, because it's 3625 if I kept going, and because I only have a table that's only good to 4 decimal places anyway, I'll ignore the 25 and just simply write 3396. So that is the logarithm of b base 10. And so b would be equal to 10 to that power, 10 to the 0.3396. Now to take the anti-logarithm, we will use a table and go the other direction. So 3396, by coincidence, it is in between here, between these two marks here in light gray. So 2.18, so this is the 8 column. 2.18 goes with 3385. So let me clear out some space here so I can write this down. So 2.18 goes with 0.3385. And the other one, 2.19, goes with the next number, which is 3404. And what I want is 0.3396. And so the question is, what is the x that goes with it? Clearly it's 2.18 something. So let's figure out the line between here, y minus 0.3385 is equal to the slope. The slope is 0.3404 minus 0.3385 is 0.0019 divided by 0.001. Then we have x minus 2.18. Now, the y in question is 0.3396. So if I plug in 0.3396 for y, that gives me 0.0011. And then I need to divide that by 0.0019 and multiply that by 0.01, and that gives me x minus 2.18. So x is equal to 2.18 plus whatever this is. 11 divided by 19. We can do that real quick, and I'm going to cheat and use the calculator for that. 11 divided by 19 is equal to 0.5789 plus 0.01, or times 0.01 is 0.0058. And so x would be equal to 2.1858. So 2.1858 would be the anti-logarithm of 0.3396. So my answer for B is 2.1858. Okay, now let's go back to the technology and see if this actually worked. If I simply take 10 raised to the 0.3396, lo and behold, I get 2.1857, so I'm off in the last decimal spot. And finally, to check to see if the whole thing worked, let me go back to the original problem, 22.83, and raise it to the 0.25 power. Indeed, I get 2.1859, so I'm off in the 10,000th place. Okay, so that's how to do these problems, and a little taste of how computations were done, a generation or two ago without the use of an electronic calculator.